In this video about atomic structure in isotopes, we're going to go through the calculations necessary and definitions necessary for this section. And we're also going to go over mass spectrometry in a short bit of detail. And we're also going to talk about some relative terms that you're going to use. Now, let's carry on. So, the first thing though we're going to talk about is the development of the model of the atom. Now, around 400 BC, Democritus thought that atoms were indivisible. Okay, and then from then on, nothing much happened until we got to Dalton around 1800, and he said that atoms of the same type have the same atomic weight. Okay, then we went to J.J. Thomson. J.J. Thomson around 1897 said that atoms contain electrons spread through a sea of positive charge, so basically a sphere of positive charge. He called that the plum pudding model, so this sphere of positive charge, which has negative electrons spread throughout it. Okay. In around 1909, Ernest Rutherford decided that atoms have centrally positively charged nucleus surrounded by orbiting negatively charged electrons. Now he did that through a gold foil experiment. So he had a piece of gold foil, he then fired helium nuclei at it. Helium nuclei, most of it went through. This is a GCSE topic, and most of them went through, and that means that most of the atom is empty space. And he found that some of them were deflected, so that's helium nuclei, that's He2+. So the 2+ ions bounced off the nucleus. So he said that there was a densely packed positive nucleus, lots of empty space, and then electrons going around the outside. That was his model. Then we went on to Henry Moseley around 1913, and he determined atomic numbers, and that led to the periodic table being ordered. And then we have Niels Bohr, who basically developed something called emission spectra, which is basically where you shine a certain frequency of light at an element, and then it will emit a certain amount of light back. And he found out that because those different frequencies of light were given out, that means that the electrons must be promoted to certain energy levels, and then when they fall back down again, give out a certain pocket of energy. And so therefore that proved that the energy levels were there, because you can't promote the electrons up and fall down unless you have energy levels in the first place. Okay, so that's how we got our shells that you normally see. Then you have de Broglie and Schrödinger, okay, and they found out about wave-particle duality, and therefore that led on to be able to come up with atomic orbitals. The last thing is James Chadwick discovered neutrons. Now you notice on any of these I haven't gone into a huge amount of detail. I've talked you through them because you don't really need to know a huge amount of detail. You do need to recognise what the models look like though. And that's what we're going to do next. We're going to talk about them in terms of what they actually looked like. So let's start with Democritus. Okay? If we look at this, we can see that he developed the atom. Okay, and said, well, he didn't develop the atom, but he said that atoms existed. Okay, and then we go from there and we go all the way to J.J. Thomson's model. J.J. Thomson's model is this big sphere of positive charge dotted with electrons all the way through it. Okay, now we then go to Rutherford. That is as the result of the helium nuclei gold foil experiment. Again, I'm not talking too much about the tests because the tests aren't really assessed. Okay. But I'm looking at the models, and it's much easier to draw out the models. So if you're revising, I would draw out the models. Really helps. Okay. If you look here, lots of empty space, very densely packed positive nucleus, and these electrons go around the outside. Next one, and this is Bohr when he decided that there were shells. So he used these emission spectra. Remember, these electrons jump up to the next energy level, then fall back down again, and that meant that he knew that there were energy levels. And you can see here, here's the nucleus, and here's the energy levels. And this is starting to look like what you think of the atomic structure today. We then go to the point where de Broglie and Schrödinger did their wave-particle duality, which led to the work that then determined atomic orbitals. So if we look here, we've got two atomic orbitals underneath. And this atomic orbital here, which you'll know in a future video or in your course, is an s orbital. It's a sphere shape. Okay. And this one is a p orbital, which is a dumbbell shape. Okay, so both of those can hold up to 2 electrons, which is why when you look at the modern atomic structure, you can see that there are a pair of electrons each time. So a pair of electrons. And that's because a pair of electrons can fit into an atomic orbital. One orbital, 2 electrons. Last one. And again, during these two models, you obviously have Moseley, who determined the number of protons. But you have these green particles that are appearing. This is your neutrons, and this is Chadwick. And so you can see from this diagram here, you can see this graduation of the atomic structure and the model of the atom, okay, over many years. So we now end up with a model of the atom with protons and neutrons and electrons going around the outside. But if we're going to move further, we need to know what the charges and the masses are of all of those protons, neutrons and electrons. Now, the electron has charge of -1, which hopefully we're aware of already from GCSE, and a proton +1. Okay, and again, positive proton, okay, which is how I remember that. And then neutral neutron, so is 0. The important thing for this video and other videos is really these masses, and to make sure that when it comes to calculations anyway, that you understand that a proton has a mass of 1, which is an atomic mass unit, just 1, okay, and a neutron has a mass of 1. The mass of an electron is 0.00054. Now, there are many masses of electrons going around, which are usually 1 over 1,840 or 1 over 1,836. We've just chosen one answer here because we know that is the one that will be accepted in your exam. Okay, now the mass of an electron is not as important as long as you know it's very tiny, very negligible, okay, and that it may be used in certain questions, but often is not required to be remembered. It's just something that you use within a question. Now, this is a required definition. So we talk about isotopes. Isotopes are atoms of the same element with different numbers of neutrons and different masses, okay? Now, if we look at isotopes, we want to see how many neutrons there are. We want to determine the number of neutrons, and that is most likely going to be the question that you will have. So we're going to talk about two different isotopes. So we're going to go for oxygen 16, and we're going to go for oxygen 18. Okay, now oxygen 16 is the normal one on the periodic table, okay, which is the one on there. Okay, and all we do is we look at that and we look at our symbol on the periodic table and we go, right, okay, we have got an atomic number of 8. That means that we have 8 protons. Now they are both oxygen, so therefore they will both have 8 protons. We then look at that and we go, well, how many electrons? Well, they're the element, so because they're the element, they have the same number of electrons. So there's the same number of electrons. If you're ever asked to compare the differences and the contrast, you have to do this kind of thing, go up and down, up and down. Okay, and then we look at the neutrons. So the neutrons are taking the mass number. We know the mass number is 16. Okay, so we know that the mass number is 16. We take the mass number and we take away the atomic number. The atomic number is 8. So therefore, we have 8 neutrons. We then do the same thing. We take the mass number. The mass number this time is 18. Okay, so the mass number is 18. So it's 18 minus the atomic number, which is 8, which means we have 10 neutrons. So when we have an element, okay, so when we have an element, we have 2 isotopes of that element, okay, there are different number of neutrons in each, but they have the same number of protons because they're the same element. Hence, the definition, same element, different number of neutrons, and different masses. Okay? The next example we're going to do of an isotope is going to be ions. So we've picked scandium here. So I'm going to look at a scandium 3+, because you have to know about the isotopes of ions as well. So we've got scandium 3+ there. Okay, first of all, we need to decide the number of protons. That's very simple because we go to the periodic table. We know we've got 21, that's our atomic number. So that's 21 protons, okay? Now this is the difficult bit. The difficult bit is when we're looking at this, we can go, right, okay, how many electrons are there? Now we haven't done ionic bonding yet, but you've done it at GCSE, So hopefully you should know that if you have scandium 3+, that means it's lost 3 electrons. So because it's lost 3 electrons, we take 3 electrons away from what we'd normally have. We normally have 21. So we take away 3 from 21. That leaves us with 18 electrons. Okay, so we've got 18 electrons. That 18 electrons means we've lost 3 because it's 3+. Now we're now going to do the number of neutrons. The number of neutrons, remember, is the mass number, 45, take away the atomic number, which is 21. Okay, so 45 take away 21 is 24. Okay, so we have 24 neutrons. Right, we're going to do the next one. So this time selenium. Now selenium has an Se2- ion. So we've got an Se2- ion. The Se2- ion, we're doing the opposite direction, gaining electrons this time. So we're going to look at it and go, what's happening in this isotope? Okay, what's happening in this isotope is the protons must be 34. Okay, so we have 34p plus. Okay, and then we're going to say how many electrons. Now, normally we'd have to have 34 electrons if we're having neutral, but the 34 electrons has had 2 electrons added because it's 2 minus, so it's 36 electrons. Okay, then we do the number of neutrons. So the number of neutrons is going to be 79. Take away 34. Okay, so 79 take away 34 is 45. So that's 45 neutrons. Okay, so we have the ion and the number of electrons, protons, and neutrons for both of these examples. And it's most likely in the exam you will get a table. That table will just have a couple of these, and you'll just have to list the protons, neutrons, and electrons, whether they're an ion or they are an element. Now we're going to talk about relative molecular mass and relative formula mass. At GCSE, you would have used relative formula mass for the mass of simple molecules. You're not. You're going to use relative molecular mass now, which is also shortened to MR, for simple molecules such as NH3, CO2, etc. Okay. Now, relative formula mass will only be used for giant structures, and those giant ones include diamond graphite, silicon dioxide, and buckyballs or Buckminster fullerenes. Again, that's not really used very much, so do not worry too much about that, but that's where the two terms are going to be used. Relative isotopic mass is a required definition. So if you look here, we have that the relative isotopic mass is the mass of an atom compared with a 1/12 of the mass of carbon-12. So our reference is carbon-12. Okay. Now the main thing people miss off when we look at exams and when marking exams is the word atom. So make sure you put the word atom in there. Now, when we talk about relative isotopic mass, what is it? I know there's a definition, but actually what is it? Well, it's the mass number of the individual isotopes. So we've got 3 isotopes here, and it's just that mass number of those different isotopes. Now we can use the mass number of the individual isotopes to work out relative atomic mass. Now again, that is a required definition. So it is the weighted mean mass of an atom, of an element, relative to 1/12 the mass of carbon-12. Now it's split into 3 marks generally. So you've got to do the weighted mean mass, you've got to do the 1/12 and carbon-12. So they're mainly the 3 points. But again, don't forget to put the word atom in. Now you can also work out the atomic mass once you're given the percentages of each of the relative isotopic mass. So if we look here and we can go, here is bromine, we're going to try and work out what the relative atomic mass of bromine is. So the relative atomic mass, so we put AR, and in brackets bromine. It's always good to write it out in a very systematic way. Okay, and we look at that, and what we do is we take the relative isotopic mass, which is 79, and we times that against the percentage. So imagine there's 100 atoms. So there's 100 atoms, but 50.686% of those, or 50.686 atoms, okay, are 79. Okay? And then what we do is we add that. to 81. Okay, and that's 81 times 49.314. Okay, so we're taking the mass, the relative isotopic mass, and timesing it by, for example, the percentage or the number of atoms if we had 100 atoms. So if we had 100 atoms, 50.686 of them would be this. Now, if there's 100 atoms, we have to take an average. Remember, it's a weighted mean mass. So here's your weight, and we need to turn this into a mean mass. Okay, so what we do is, to do that, we divide by how many atoms we're trying to take it the average of, and the number of atoms, if we're saying there are 100 atoms here, is 100. Okay, if that is the case, okay, you end up having this calculation to be 79.99. Okay, notice that I have rounded it to 2 decimal places. So that's our exam tip for this one. Always round the AR to 2 decimal places. So this is your relative atomic mass of Br. Okay. So we are going to practice a further question that is mainly done in the second year of A levels. Okay. So the 2 types of questions, the one you've done before, which is just calculating the atomic mass, more likely in AS. Okay, and the second one's more likely in A2. So a sample of strontium was found to have a relative atomic mass of 87.689. Don't be surprised if that's different from the periodic table. Okay. Now, the sample consisted of 15.55% strontium-86, okay, and 1 other isotope. Can you determine the mass of the other isotope of strontium in the sample? So what you have to do, okay, is look at what you've got in the question. You've got an atomic mass, okay? You've also got one of the isotopes, and you've got one of the percentages of the other isotope. Not only that, it is 100%, and there's 2 isotopes. So what you can do is take 100, take away 15.55, and it will give you the percentage of the other isotope. So you've got the percentage of both isotopes, but the identity in terms of the mass of 1. So you can put that into the equation we've been using in the last few slides, okay? And you can look at it and go, right, here we are. 87.689 is the value that I got from the question, okay? So from the question, okay? And then we've got 15.55, again, from the question, okay, over there. And then we've got 86 from the question, and we've got our 84.45 that we worked out because we did a 100 to take away 15.55. Okay, we then all divided that by 100 because it's an average weighted mean mass. Okay, we rearrange that by timesing this value by 100 to get rid of the 100, and we've got rid of the 100 there. Okay, and now we've got 8,768.9. We then minus away the 1373.3, and we've minused it away here, and then that gives us 84.45 times A. Now 84, if you then divide by the 84.45, which we've done here, okay, you can see that we get 88. So our answer is 88. Really important here as well, I haven't focused on the last few slides, but look at that unit, grams per mole, grams per mole, grams per mole. That's the units of relative atomic mass, and that's the units of relative isotopic mass. Now, we are going to do the final type of question on this, and the final type of question on this is finding the relative atomic mass of chlorine using something called mass spectrometry. Mass spectrometry is basically an analytical piece of equipment, which means that you can find out the relative abundance of different isotopes. So if we look here, you'll see I've got something called MZ down the bottom. Now the MZ value is equal to the atomic mass of the isotopes. That's all you need to know for now. So if you look there, 34, 35, 36, 37, 38, 39, they're the atomic masses of the different isotopes. Now notice there is a peak at 35, there is a peak at 37. Now what we have to do, and this is our tip, our exam tip for this section, is you have to get your ruler out. So if you're in an exam and you get presented with this, you've got to get your ruler out. So get your ruler out, measure the line, and find out what the proportion is between the two. So we measured this line, okay, and we found, and like it's showing with the ruler here, and then we measured the next line, and we found they're in a ratio of 3:1. Now, because I'm going to try and keep it quite simple, I'm going to say, well, 3:1, what's 3:1 in terms of 100? Because we have got We've been using 100 all the way throughout here. You don't have to use 100, but we can show this relatively and say, okay, this is 75%, okay, and this one down here is 25%. Again, because they're in the ratio of 3 to 1, okay? So 3 to 1 is 75 to 25, okay? So that means now we've got the masses of the different isotopes and we've got the percentages all from this mass spectrum. So all we do is we calculate our AR. So our AR of chlorine, okay, is going to be 75 times, and we go down here and we look for the 35. Okay, plus 25 times, this time 37. Okay, and then we divide that all by 100. Okay, if we divide that all by 100, you end up with a value of, okay, let's choose a different pen here. Okay, 35.5. And remember, we're always doing it to 2 decimal places, so I'm going to do it 35.50. And the unit again, just to remind you, is grams per mole. Okay, so we have 3 types of questions. One where you just calculate the atomic mass relative atomic mass, because you're given the values to put into this equation. One is where you've got to find the mass of one of the isotopes, and the other one is when you get a mass spectrum just like this, and you can get the values off the mass spectrum and work out the relative atomic mass that way.